Hope everyone's doing well whatever time zone it is for you who's joining. Being a little sneak peek there. Yeah, today I think just as a quick overview, we'll be going over, like Rebecca said, building OmniChain tokens, understanding a little bit deeper how Ethena's implementation works, and ultimately implementing your own OmniChain fungible token and learning how you can start sending tokens cross-chain starting today. So without further ado, my name is Matt. I'm developer ecosystem lead at LayerZero Labs. If you want to follow me, I'm at Uncrackable on Twitter or X. And before we kind of jump into LayerZero, let's take a step back and actually look at Ethena's OmniChain fungible tokens, USDE, SUSDE, and Ethena. All three of these tokens have done around $600 million roughly of value transferred in the past 60 days. And they overall have a fully diluted value of $8.1 billion. So for these for these tokens to be able to amass such a high amount of value and also be able to secure that value transferred, there needs to be some significant improvement in the sense of how security is done at a cross-chain level, the ability to move that value seamlessly for both the UX of the holder of these tokens, as well as from the application perspective, the ability to seamlessly connect any new network that they want to bring this value transfer to. At a high level, the way that Ethena does this is using LayerZero. LayerZero is thought of as a global ledger. It's a way for you to have permissionless, censorship-resistant, immutable bridge infrastructure, flat out. At a bit of a deeper level, LayerZero itself is an immutable interoperability protocol for building universal blockchain applications. What does that actually mean? For LayerZero, the way that it works is that any application can be deployed on a source blockchain and a destination blockchain, connected together using some application-specific parameters. And any application can send a message in the form of bytes, a destination chain that they want to go to, and choose the security stack of different verifier networks that validate essentially whether that transaction is valid, and then have it automatically executed on the user's behalf on the destination chain. And so this framework for interoperability enables you to build very, very diverse applications across multiple networks. The way that I like to think about it, and maybe to zoom out about bridging in general, is to compare it to a real world example. The reason bridges are so valuable is that they connect isolated groups of people. And more importantly than the isolated groups of people, they connect their information. And the ability to coordinate this information between isolated parties means that you suddenly are able to unlock really cool things like the transfer of goods and services, and ultimately power financial applications based on the transfer of those services, goods, information, etc. When we talk about blockchain in today's world, the same trade-offs kind of appear. Every single blockchain is an isolated island you can think of, and each of these islands have their own standard for speed, cost, security, different network semantics, different applications built on top of them, different communities, different funds. The list kind of goes on. And so this isn't fully accurate, but you can kind of see here that there's a clear distinction that starts to get made as you look at more and more networks. And over the last year, we've started to see more and more developers to dip their toe into these different networks, mainly because there are just different opportunities for you as an app builder, depending on the chain that you go to. But we have to understand, I think, before jumping into cross-chain, a little bit more about how the base ERC20 transfer works. On a single blockchain, for example, Linea, ERC20 transfers are very straightforward. Whenever I send tokens, really what's happening is I'm saying to debit an amount from my address and update this mapping that controls how many tokens I actually own, and then credit those tokens to the target address that I want to send to. And this is really easily done within a blockchain because everything is atomic. Either the whole transaction succeeds or the whole transaction reverts. But as soon as you move to a cross-chain world, that immediately becomes a little bit more complicated. Suddenly, I have these two isolated networks that don't know about each other. And so I have to figure out a way for me, the app developer, to initiate a transfer on a source blockchain, ensure that that state change is final, it's not going to revert or roll back at some point, and then bring notification about that state change to a destination network. And finally, once that notification has been processed, receive those tokens to the target address that I want to on destination. If you were listening so far, you might have already thought about some of the complications that can arise with a system like this. For example, what happens if someone gains control of the system and is able to infinitely receive tokens? There's a lot of downside risks that can be played if you don't have secure pathways for messaging between chain A and chain B. And so historically, the way that this worked was with a concept of monolithic bridge security, this idea that I can have some third party that I trust that is listening to messages for me and will deliver them to the destination chain on my behalf. And you can think about this monolithic bridge security as a centralized provider that is fully trustful in the sense that it will be a centralized entity listening to events on the source chain and directly writing them to the destination. You can think about this as a permissioned set of validators. So in the sense of a controlled group that there's maybe 3 or 4 different parties, but I don't have a say in who they are. Or you can think of this as a middle chain bridge where this verification layer is literally another chain underneath. But regardless of the verification technique used, there's always one very critical downside that often got overlooked. What happens when that security fails? Well, not only was your application put at risk, but every application that was trusting that validator set was also put at risk at the same time. And it's part of the reason that over the last, I would say, decade, we've seen the largest exploits in the blockchain industry all related to this type of monolithic bridge security. Bridge hacks are some of the most notorious and also some of the most costly for app developers and users. And so understanding what causes these events to arise is really, really valuable from a developer point of view. And generally speaking, the reason that there's been so much value lost is that in these examples, every application is forced to use the same channel. When I say channel, I mean a direct pathway from Ethereum to Base, for example, where you are trusting this one validator set to secure every single transaction that is sent across the pathway. And when we think about this a little bit deeper, it also forces app developers into a very kind of nasty trade-off. You're forced to basically accept when you're picking your cross-chain interoperability provider, point A or point B on the security cost curve. You either can pick an app that has a low security threshold and an equally low cost for fees to send messages to a new chain, or you can pick a network that has a very high cost associated with the cross-chain messaging fees and an arbitrarily high level of security. Obviously, things get a little bit more complicated. It's not exactly linear, as I'm showing here, but the main takeaway is that switching costs for dApps are very, very high. If you pick point A or you pick point B, typically there's a lot of danger involved with ripping out your cross-chain interoperability provider and supplementing a new one in directly. It requires typically core contract changes, re-audits, redeployments, and you always run the risk of accidentally implementing incorrect messaging and potentially breaking your application and all of your users on top of it. That's why I like to say, if you think of Ethereum as a dark forest, you can think of cross-chain as a dark ocean. You have these islands of interoperability where if a malicious actor controls the port and all of the waterways to that island faces an existential threat. And similarly, if a centralized entity accidentally breaks the port outright, the island also faces an existential threat because no one can actually land messages there. So zooming out a little bit, what does that actually mean for LayerZero? LayerZero at a protocol level is comprised of 3 main pieces. First, this idea of OmniChain messaging. It's the ability for any application to interact with an immutable contract interface known as the LayerZero endpoint and configure all of the messaging properties that they need directly on chain. When you interact with a LayerZero endpoint, you can select a custom amount of verifier networks that you want as part of your security stack, threshold for security, and you can ultimately decide the type of security that you're using. These verifiers could be the native bridge for Arbitrum, for example. They could be a provider like LayerZero Labs running traditional node infrastructure. They could be another generic message passing protocol like Axelar. The point is that, broadly speaking, the protocol interface is broad enough where you can use any type of validation you want to power your cross-chain messaging, including yourself if you want. The second piece built on top of the core protocol is this concept of automated function calls. Using LayerZero, you can pay a fee to an executor to automatically deliver messages on your behalf and source the required destination gas token for users all without having to leave your source chain. What that means is that while you have secure validation on the first part of the stack, the second part of the stack actually makes it a lot more seamless and makes the UX a lot nicer for you to abstract away all of these destination networks, and makes it a lot more straightforward for developers who are building on top of you. And finally, the most important piece that you'll be working on during this hackathon, the actual smart contract layer. LayerZero provides a contract library comprised of 3 different cross-chain standards. The first being OAP, which provides essentially a lot of helper functions and security checks around what you might want at the application level for sending and receiving messages. OFT, the OmniChain fungible token standard used by Ethena, which enables you to move ERC20 token balances cross-chain. And finally, ONFT, the ERC721 cross-chain variant of this standard. So overall, there's a lot of room for you to expand and not even use these standards, but actually build your own. At a high level, the way that this workflow actually behaves is that an application will decide on a message that they want to send in the form of bytes. You will select a destination chain in the form of an endpoint identifier, and you'll provide a configuration in what's called a send library. This send library stores your configuration on chain, and using the endpoint contract will essentially pay fees to your designated security stack, this collection of verifier networks, as well as to your executor, and is also emitting an event off chain for them to listen to. Once that message has been emitted from the source chain, these security stacks will then go and write verification onto the destination network, which your application has set in order to enforce specific properties about what is the threshold for verification. You can enforce the number of block confirmations these verifiers have to wait. You can enforce the addresses that they need to have. And you can also, again, enforce which ones are required and always needed to sign off, or some that are optional. The point being is that you are configuring your security threshold based on the providers that you set. Once verification has been marked as valid, you can then permissionlessly execute this message to the destination chain. Typically, the way that this works is that a LayerZero executor will automatically deliver this message for you directly, but this is also permissionless as a call. So anyone can run an executor and anyone can call the endpoint directly once the message has been verified in order to deliver their asset. And so this framework essentially builds to how LayerZero as a protocol works. This immutable cross-chain interface combined with a modular security stack enables you to not only own point A and point B as configuration options for your application, but also every point in between. And the unique unlock that this provides is that as security improves, say for example, with ZK bridging that we've seen over the last 2 years, as new validation techniques come online, applications can optionally opt in to this new set of validation, improving their security, keeping the same cost they already have or reducing cost overall, and ultimately not have to redeploy their entire application because of a new messaging pattern that they want to use. Overall, what we see today in the marketplace for LayerZero, there are over 30 plus different decentralized verifier networks. These can be ZK-like clients, they can be cryptographically secure state proofs, they can be other messaging service providers like Chainlink or Axelar, they could be Web2 entities. The point here is that not only is there a broad diversity when it comes to the number of validators that you can pick from, there's also infinite expansion of this set. Anyone can run a DVN permissionlessly and use any type of validator set that they want to use. And so it enables you, the app developer, to have tons of flexibility around the construction of this security for your app. Besides the security set, LayerZero again allows you to abstract away gas for your users. Users can pay only in a source chain token and have that token automatically swapped for them for their destination transaction. And this was really cool because you can coordinate a lot of advanced token transfers where you need gas limit in the user's wallet, or you need gas limit or message value in your application call in order for it to execute properly. And more so than just the gas drop, LayerZero's execution enables you to have 2 distinct modes of composability. When we talk about composability, one of the big things that we typically see is that when you have a cross-chain call, let's say I'm delivering my tokens to a destination chain, I will want to call 1, 2, maybe 3 other smart contracts within that destination call. Let's say for a token transfer, this is a call to swap, stake, and maybe some other third operation that we have afterwards. The problem with this type of atomic composability or vertical composability is that if, let's say, the call to cross-chain contract C fails, the entire call stack reverts, meaning that we didn't get our token delivered, we didn't get our swap performed, and overall, this just leads to a very bad UX for the developer and for the user trying to figure out what went wrong in the cross-chain stack. The way that LayerZero addresses this is with the concept of horizontal composability, the ability to essentially slice up my destination transaction into little composable bits of what I want to have happening. So in this example, let's say that this first transaction being executed is the token delivery. In this same call, I will re-ping the LayerZero endpoint and tell the executor to execute a second transaction entirely separate from the first one. And what's really cool here is that this flow allows me to say, mint my tokens to the address that I expect, but if something goes wrong in a secondary call, I am safe knowing that the first operation at least succeeded, and there are still paths for my application and my user to go down, even though the second half of this call reverted. So overall, this builds to what we think of as an OmniChain application for LayerZero. It's the idea that any smart contract on any blockchain network can use a LayerZero endpoint to seamlessly send messages using whatever type of trust assumption you want. LayerZero is basically built as an immutable protocol stack that is agnostic entirely to the type of verification that you use and the type of execution that you use. And doing so enables you to seamlessly plug and play any type of app use case that requires cross-chain messaging directly in and start using it today without talking to anyone. So with that in mind, let's actually jump into a live coding example. Right here, what I have pulled up is a very simple repo. This is the, let me just close that. This is a very simple repo that I'm going to spin up. It is from LayerZero CLI tool. I'm going to run a very simple npx create LZ OAP at latest. This npx package is our CLI. It will pull in a Foundry and hard hat specific repo for you to build off of for the hackathon. And I highly recommend you take advantage of this. It just builds in a lot of really nice utilities for managing some of these security properties that you have with the protocol. When I run this command, what it will prompt me with is it asks to, create my project. I'll call this my LZ OFT. And it'll give me a selection of different contract standards to start from. For this example, I'll start with OFT, assuming that I'm deploying a brand new token. It'll ask me again what my packages are that I want to use. I'll say yes to installing everything, and it will kick off just pulling all these dependencies down for me. And what's really cool here is that in this kind of sample code space, you'll be able to see very, very quickly some of the utilities that we bring in for you. For developers who are familiar with ERC20, this will be really straightforward for a lot of you. LayerZero simply extends the ERC20 standard with the ability to, perfect. We're going to just open this folder up. Perfect, got my .env. Oh, I need to go one level deeper, right? We'll do my LZOFT, copy and paste that .env file in, just git initialize this so I don't accidentally push my .env file anywhere. Perfect. So looking a little bit closer at what is brought for you in this sample repo, my OFT is a very simple contract. It is simply extending the base OFT standard. And if we look inside the OFT, OFT is simply a combination of some core bridging logic in OFT core, along with the basic vanilla ERC20 token standard. And if we look a little bit deeper, we can see a little bit more how this works. OFT is comprised of two internal functions that get called whenever you send a message. Debit, which calls the ERC20 burn method to burn an amount of tokens, and credit, an internal function again that gets called when you receive messages to mint an amount of tokens to a specific address. Looking a little bit deeper for my friends who want to go even deeper into the call stack, the way that these calls are made is that in OFT core, there is a send function here Send basically returns this internal send. Internal send calls this debit method. And then if we jump really quick to our LZ receive, this is the function that gets called on the destination network anytime we're receiving. And that credit method is called again here, along with that composed message example that I talked about earlier. So at a high level, all OFT is doing under the hood is taking a vanilla ERC20 token, defining some logic on how to send messages, and defining some logic on how to receive messages. So yeah, this is a high-level overview of how the contracts actually look. Let's explain a little bit more what comes in this repo and how we can get started. For example, if I wanted to deploy these outright, I'm going to just define a very simple line here in my constructor to mint 100 Ether to me when I deploy this contract. We'll do actually pnpm compile. pnpm compile, if you're wondering, just pulls scripts from our package.json. You can see here that pnpm compile is simply running forage build as well as npx hardhat compile. So that's really all that's happening here. The reason that we have both of these is actually that the protocol extends a package that might be popular and familiar to you, hardhat deploy. The way that it works is pretty straightforward. When we go into our hardhat config here, let's say that I want to, instead of deploying to Avalanche and Polygon Amoy, I'll get rid of Amoy for now. I want to make this Arbitrum Sepolia testnet. The way that I'll go about deploying to Arbitrum Sepolia is I'll first provide an endpoint ID. We'll jump in and do arbsep v2 testnet. This is a package that gets automatically pulled in for you. We'll do rpc URL arbsep. I don't have one directly in my .env and would not like to run myself, but where we can easily find all of these nice RPCs for us is chain lists. So just tick include testnet. For those of you who are watching at home, type in the name of the chain that you're looking for, in this case, Arbitrum Sepolia, and you should be able to pull up very quickly here a free public RPC that you can use for your project. Jumping back in, I'll copy and paste that RPC in. We now have it set in our hardhat config. Looks great. And the next thing that we'll do is actually go about deploying these contracts. So I want to deploy my OFT on Arbitrum Sepolia and Sepolia. To do this, I'll run npx hardhat lz deploy. When I run this command, what it'll do is it'll pull up essentially a prompt window with the chains that I want to deploy to. In this case, both of these look great. Let's just review our hardhat config one more time to make sure that indeed we are deploying on Sepolia and Arbitrum Sepolia for V2. Hit enter. It'll ask us what deploy script we want to use. In this case, you can see here in the deployments folder, we have a MyOFT script that is using the MyOFT contract right here. We'll hit enter. It'll find the two networks that we're using, arbsep testnet and Sepolia testnet. We'll hit yes. We'll get some deployer addresses pulled up here. In this case, this is my private wallet. And all things going well, we should get two new deployments that appear in our deployments folder here. And if you run into any issues during this process, just remember, it could be due to your public RPC. There are some public RPCs that, again, can be spotty. Testnet is always, a little bit of a play around and find out if it works. So if you run into issues related to RPC errors here, try switching out your RPC for another one of the available ones on Chainlist. There are always a bunch of them that are being up to date, and you will generally be able to find one relatively quickly. This deployment's taking a little bit longer, but in the meantime, what we can do is go, I think, a little bit deeper into what else is coming in this repo. So in addition to our hardhat config, like I showed you here, that sets up our initial project for hardhat and gets everything spun up in terms of the networks, we also have this file called LayerZero config. LayerZero config is pretty interesting. What LayerZero config enables is basically a way for you to define, sort of like a makefile, all of the contracts that you have deployed on different networks. In this case, I've defined here Sepolia contract with the Sepolia v2 testnet EID. I've defined the Fuji contract with the Avalanche v2 testnet, the Amoy contract, and so on. It looks like we are hanging on. Which chain exactly? It looks like we have it deployed to arbsep. Let's just confirm this by going to Arbitrum Scan, jumping over to Sepolia, pasting this address in. Let's confirm it's a contract. Great. Yeah, so we can see a minute ago, contract creation. So this contract does indeed exist. It seems that our Sepolia RPC is hanging a little bit. Same thing here. If you run into any issues like this, again, you can pop in the chain list. We'll do Ethereum Sepolia. Actually, I think it's just Sepolia on this list. Great. You'll probably see it towards the bottom here. We'll jump through. There's a lot of Sepolia chains now, so there's always some to jump through. Linea, Arbitrum. I'm not seeing Ethereum Sepolia, but it also is early in the morning for me, so maybe I am missing it. Still loading there. Let's see if we can do Ethereum. Sepolia. If we close, there we go. Okay. It was just blocked by the drop-down window. Classic. Here we are. So again, tons of different Sepolia RPCs for us to take advantage of. I will grab a Tenderly one. In my experience, Tenderly is usually pretty good. Again, we'll close this out. We know that one of our deployments succeeded at least. We'll throw our RPC for Sepolia back in here. Let's try this one more time. So npx hardhat LZ deploy. Now we can select just Sepolia. We'll use my OFT, hit continue. And hopefully this one goes by a little bit quicker now that we have a different RPC. The other thing to keep in mind too for doing testnet deployments is the Sepolia GUI price. So if you look right now, hopefully it hasn't spiked like crazy. Nice. In this case, we seem to be good. Sepolia can have often a huge spike in terms of the cost you're paying per unit of gas. So just keep in mind that when you're on your testnets, chains with very heavy demand might have higher fees associated with them due to these spikes. But great, it looks like we deployed the Sepolia testnet now. Let's just go and confirm. And perfect, we have Arbitrum Sepolia and Sepolia testnet. So we'll close out of our hard hat config. The next thing that we want to do is actually connect these contracts now that they're here. So to do that, I'm going to run npx hardhat, and I'm going to run LZ OAP config init. It will ask for two params, a contract name, in this case, my OFT, and also the name of the file that I want to create that has these configurations. In this case, I'll call this new LayerZero config.ts. This will go ahead and run. It'll ask me which networks I want to configure, Arbitrum Sepolia and Sepolia, and it'll create this file locally, new.LayerZero config. Let's actually format this just so we can see it a little better. You can see here that in this setup file, it's defined for me my two contracts, arbsep and Sepolia, and then defined the configuration for Arbitrum to Sepolia, both the send configuration as well as this receive configuration, and also for Sepolia to Arbitrum Sepolia. So it's defined the send configuration and the receive configuration. And this makes sense because you need to have configurations in both directions, right? So you can think of it, whenever it says from, this is the connection set on Arbitrum Sepolia. And similarly, when you see from here, from Sepolia testnet, this is the connection set on Ethereum Sepolia. So now that we have this configuration, how do we actually wire these things together? We're going to do npx hardhat LZ OAP wire, OAP config, new.LayerZero config.ts. We're going to run this once. What will happen here is it'll read this file and then compare the configuration that we have in this file with the configuration that we have set on chain. And after it compares them, it'll say that I have 10 transactions that I need to run. You can look through all of them here if you're curious. I'm going to trust it and hit sign. This may take a moment just because you're submitting 10 transactions on chain. But the really neat thing here is that you are able to fairly quickly get started with a sample transaction. The other thing that I'm going to do here is I'm going to create a quick task folder. So tasks are basically a way for you to, write scripts in Hardhat. You can also do the normal Foundry scripting process if you wanted to. And I'm going to call this send.ts. And what I'm going to do is actually pop into the LayerZero docs, docs.layerzero.network, go to EVM, go to my OFT section, pop into calling send, and I'm just going to pull this Hardhat task that I already have set up here. There might be some error messages about imports. Hopefully everything is pretty straightforward. Nice, nothing too crazy. And the only other part to add here is we're going to import our new task that we just added. So we're going to import tasks/send, and actually we'll just make sure that it knows to look for this. You can see here, we just finished signing all of those transactions. We can confirm this by jumping back over to Arbitrum Sepolia Scan and refreshing this page. You can see that a method was called setPeer on the contract itself. This notifies you that, hey, we are ready to get started sending messages between these contracts. And the second step that I'll do is I'll just run npx hardhat one more time to kind of see what tasks are available. And hopefully we should see LZ OFT send. Nice. So what is this hardhat task actually doing? Jumping back over here to send.ts, you're specifying a 2 contract address on network B, a 2 EID, the endpoint identifier for that chain, and amount of tokens to send in token decimals. If you look here, you can see kind of how this gets put together. We instantiate a new contract. We get the decimals for the ERC20 token. We convert essentially our amount that we want to send from the task to these token decimals, and then generate our send param before quoting the cost, getting the fee, and calling send. So let's play around with this a little bit. We actually don't need these lines either. We're going to test our send, hardhat LZ OFT send. We're going to supply our arguments that we defined up here, this 2 first. Oh, don't want to edit the contract. We want to edit this field here. 2 is going to be our contract address on network B. In this case, we can grab that from our Arbitrum Sepolia. We'll actually call send on Arbitrum Sepolia and send it to our Sepolia contract. So we're going to send to Sepolia. We are going to use the EID for Sepolia. If you're wondering where to get that, again, can look in the LayerZero docs under supported chains and jump in here, Ethereum Sepolia 40161. And we'll grab our 2 EID, 40161. And finally, our amount, let's just put in 1 and see what happens. And we will see what's going on here. Oh, right. I'm reading literally, but if you are writing in the command line, this camel case converts actually to snake case. And 2, not underscore, 2 EID. There we go. And right, we need to actually pass in one other flag, our -- network. And in this case, arb sep testnet. So you can see here, we're sending 1 token from Arbitrum Sepolia to Arbitrum Sepolia. Or sorry, reverse, from Arbitrum Sepolia to Sepolia testnet. You'll get send transaction initiated. We can look in LayerZero Scan and actually open this up. What LayerZero Scan is doing is basically waiting for the transaction to land. and then is going to index it here for us for actually to follow through our full transaction. And we actually need to jump perfect to testnet. You can see here that the message is in flight from Arbitrum Sepolia to Sepolia. You can see our applications here, Sepolia, Arbitrum Sepolia. One mock OFT is being sent. You can see that it was sent on Arbitrum Sepolia to the burn address. And now we just have to wait for this message to get delivered. At the bottom here, if we actually compare, you can see all of the configuration settings that we had before. So send library corresponds to the send library that we set in this new LayerZero config. Here, 0x4 on Arbitrum Sepolia. We can see once this indexes and fills in, yep, 0x4, and all of the other configuration settings for each of our apps. So really, really cool to see all of this working. Once this transaction finishes up, sometimes transactions to Sepolia, for example, take a little bit longer. Let's try really quickly an inverse transaction in the opposite direction. So instead, I'm going to switch my network to Sepolia testnet. My 2E ID is going to switch as well. Instead of 40161, we can jump back into our Explorer here, grab 40231 from the Arbitrum Sepolia testnet. There we go. And then the only other param to switch is just the contract address. We can go back to our deployments folder, look in Arbitrum Sepolia testnet, grab our address, paste it in. Let's send a reverse transaction. So sending one token to network Arbitrum Sepolia, transactions initiated. Let's go ahead and open it up. This one again should be getting indexed right now. Again, sometimes these transactions can stall on Sepolia testnet just due to the amount of demand we have. Actually, a really fun way to look at this, if you just go to messages, you can see a constant stream of transactions that are coming through live. But while we're waiting, I think for Ethereum Sepolia to land, this is basically the end of the workshop. Everything that I've shown you here shows you how you can get started building an OFT, an OmniChain fungible token, how to get started using, again, NPX create LZ OAP at latest, and pulling in everything that you need in terms of contracts to start deploying. I think I'll pause there. While we're waiting for these transactions to land, are there any questions that anyone has from the chat? Oh, great. I will, yeah, Rebecca, it'd be awesome. Could you just read some of these out while I pull this up on the scan?
Yeah, I can. There's a few that have been answered as we've gone along because they're more logistical. But there was one question from, more loading. Diego has asked, is this project like available? Are you able to share it? Are people able to view the GitHub of the repo that you're looking at?
Yeah, definitely. I think this should finish up soon, but while that's going on, if you go to GitHub, LayerZero-Labs, all of the CLI examples can actually be found in a single repo. It's pinned at the top here called DevTools. When you go into DevTools, if you click examples, all of these folders are actually the live folders that get cloned directly to you when you select them. So when I selected OFT, when I ran npx create LZ OAP, it cloned me this sample repo that has, again, all of the contracts and similarly, some of the instructions here that explain, what you can do with OFT, what are the helpers in here that you can use, how to install, test your contracts. So I'll paste this over so you guys have it as a GitHub file. But yeah, definitely also recommend running the npx command as well.
Ivilo has asked from Ethena, has asked if LayerZero supports the BLE testnet, the new.
Yes, we do. So really, really good way to go and look for it is, again, if you jump to supported chains in the docs, you can show recently added. I believe BLE has been added. Yes, so we are on BLE testnet. You can find all of the contracts here. And then again, each of these will take you to a link, or you can copy them however you'd like to kind of move forward. And there we go. So we can see here that on the Explorer, from Arbitrum Sepolia to Sepolia, this transaction was delivered. And awesome, from Sepolia to Arbitrum Sepolia, this transaction was delivered. And if I check my wallet balance here, we should see, I think I have to import the token because I haven't actually added it yet. So let me just go ahead and do that. We'll grab our source token here. Go ahead and let's see. Yep, we want to import token. I do not want to back up my key right this second. All right. Well, you can see that it's delivered here. I won't pull up my MetaMask for now, but yeah, hopefully this was helpful for everyone, and it was pretty easy to get started.
Yeah, thank you for joining us. This has been a really interesting workshop. And it'll be a really useful resource, your demo. The deadline for submission is the 1st of December. So it's on a Sunday in about 3.5 weeks. So plenty of time to build.